It's a steel and concrete frame church in Anchorage, Alaska. The biggest thing for sure is its location. Obviously, the distance between Nanaimo, British Columbia and Anchorage, Alaska, and the shipping requirements to get there is huge. That's one of the biggest hurdles we had. There was zero chance that we could miss any little piece of steel because replacements aren't nearby.
We had to have a structure that could withstand the snow loads, was one of the primary reasons as to why they went with steel. The building has flat roofs. They had to be able to withstand a 5-foot snow load on the roofs is kind of what they had on their engineering calculations.
There's definitely some large spans in there that I don't think wood framing or concrete could do with the open concept.
We had everything sorted and staged up here, and it was basically an on-time delivery situation where the truck would arrive on site, it would get immediately offloaded and thrown into place on the building.
We all worked together as a team with a common goal to get this thing built in a remote area in a timely manner. It went really well.
It's just a nice facility to have in the area where people can come just walk around and admire the beauty that comes with having a structure like that in town where everybody's welcome.
It's an office building located in Bellevue, Washington, sort of oval shaped, and one of the main features of it has an offset core. So the elevators and service areas are offset, leading to a very large open floor plate that faces towards the south in the view direction.
Normally with structural steel, you'd have a concrete core and you'd build out from that. This project had a steel core. Around the perimeter of this building, we had BRB bracing going all the way up, all the way in line, and it kind of spiraled around the building as you went up.
The other advantage of steel is the building's much more lightweight, and so the overall seismic forces are less because seismic demands are proportional to building weight. So both reducing the weight and allowing for steel bracing were the main drivers of it being steel.
And steel also goes up very, very quickly. So we were being able to erect 2 floors every 3 weeks, steel erected, decked, and ready for the next floor.
It's a pretty unique building, and that's part of the architecture, but also part of the engineering. As you look in downtown Bellevue, and it stands alone as sort of a different looking building from all of the other square rectangle buildings that are in downtown.
This project is a 10-story mass timber steel hybrid structure over top of a concrete podium, and I'd say it's one of the most seismically advanced timber structures in the world.
It is the tallest unencapsulated mass timber office building up to now. We removed a lot of the shear walls from the interior floor plate, put them into brace frames in the exterior. With the structural team, integrated these really unique Tectonis seismic dampers.
The whole design was based on the concept of a beehive, and when you look at the outside, it's got that sort of beehive nature to it. Between the wood and the steel, we have over 13,000 pin connections that had to get put in, and our tolerances were less than 1 millimeter.
My hope for this project is that it acts as an example of pioneering. I think it'll be reported on for years to come and be a beacon for Canadian innovation.
Doing the unencapsulated at 10 stories, doing the Tectonis brace frames has actually helped pave the way for other mass timber projects and hopefully pave the way for other hybrid steel and mass timber projects in the future.